Okay. Hi. Good afternoon. Good evening, everyone. It's almost good night, everyone. So let us have a very quick revision within 5 minutes. Like I'll just pick up a random name and I want to understand what did we went through the last lecture. Okay. Okay. So Teja, can you just unmute yourself and just give what did we went through in the last lecture, last meeting? Teja, are you there? Guys, kindly unmute yourself and speak at least yes or no. Yeah, hi Teja. So you were there over there in the last class, correct?
Teja, just remove Teja. Remove Teja. He is not muting. Remove him.
I think he was speaking. Teja, can you speak? There was a lot of background noise.
Yes, ma'am.
Okay, so Teja, you were there in the last class, correct?
Yes, ma'am.
So just one topic, can you recall what we went through in the last class?
Floor plan, ma'am.
Pardon?
About floor plan we discussed, ma'am.
Floor plan. What did we discuss about floor plan?
Hello.
What did we discuss about floor plan?
Teja, you can mute.
Ma'am,
No, lot
I
of noise.
didn't remember that.
Yeah. Teja, you
Kalyan,
can
you were
mute.
there, correct?
Hello.
Yeah, Kalyan, you what did we go through in the last lecture? Can you just give? I just wanted a quick revision, guys, so that you're aware what did we went through. Ravichand, you are there, correct?
Yes, ma'am.
Okay, so just can you explain what did we go through in the last class?
The orientation, then site rows, the origins. The placements begin at the origin, then we place it at the appropriate locations. Then left LLX, LLY, ULX, ULY. These are what is the meaning of it? These kind of
Okay, so
things.
but indirectly we studied two major different categories of files. One is which we did was a physical
Text file.
library of standard cells, and we went to the technological library, correct?
Correct.
Okay, so in physical library, we understood, for example, there is a cell, the cells are defined through keyword macro, what is the class, what does the symmetry states. Then we understood that each pins are defined, their directions, what is their purpose of usage, whether it's used for signal or is it used for power or ground, correct? So we discussed in depth about what is a physical library with respect to standard cells. Then we understood, for example, what all is there within your technology library. Okay.
Yes.
So for example, Shiva, can you unmute yourself and let me know what's in TechLeft file?
Yes, ma'am. So in the TechLeft
Let the
file, we
screen
have,
out.
sorry.
Hello.
Yes, sir. Are you speaking something?
No, just continue.
Yeah. So in TechLeft file, we have seen what kind of metal layers we are using and what are their widths and what is the spacing we need to maintain. And
So what's the
also
difference between the spacing and the word pitch?
Yeah, so spacing will be from one edge to the starting of the next edge metal layers. I mean, whatever the space in between two metal layers after their what vertical
And
say.
what is
So
pitch?
yeah, pitch is from middle line to the next middle line of the metal layer.
Okay, it's like the distance between two tracks, you can say, right? Metal layers are
Correct,
placed in the
correct,
tracks,
correct.
correct?
Correct.
Okay, fine. So we understood all these things with related to our TechLeft file, correct? Now today, let me share my screen. Yeah. So for example, in order to understand more detail about C1, what you would have understood that there are different files that are needed for performing your synthesis. Similar files are needed even for your performing your PNR, correct? So now to understand the complete information about one of the important files, which is called as SDC, right? You need to first be very clear with what are the different terminologies which are, especially today's lecture is related with respect to the clocks. Okay. So first starting it off, I just want to give you a very small understanding. Most of you would be aware about it, but let us go in detail about understanding what are these, for example. Okay. So any one of you know what is actually, what do you term as launch flop? Can anybody of you unmute yourself and just let me know what is actually launch flop? You always say.
Flip-flop that launch the data during the active edge of the clock.
Okay. So over here, let's say, for example, I am annotating it. This as let me call this as 1, and this is called as 2. Okay. So now, which flop is called as launch flop? Launch flip-flop?
Flip-flop 1.
Okay. So now when I'm dictating with respect to this, okay, now let's say I have considered this timing path between the flip-flop 1 to flip-flop 2. In this terminology, I will say that here my flip-flop 1 is sending out the data, or say launching the data during the active edge of the clock, okay? Because maybe this flip-flop can be of either positive or negative edge triggered, correct? Correct. So whatever is the active edge of the clock, at that time, this flop 1 launches my data or sends out the data from this Q pin. Okay. Similarly, what would be a capture flop? What could be a capture flop?
Yeah, which
That receives the data during the active edge of the clock.
Yeah. So the flip-flop which is at the receiving end, or which we say the capture the data signal. Okay. Now, for example, if you look at a very bigger picture, right, in the industries, it is not always that the flip-flop 1 will be always a launch data. Let's assume that back around there was a flip-flop over here, back around there was a flop over here, right? But whenever we are dealing with respect to a particular path, that time one flop will become as a launch, other will become as a capture. For example, there was a flop, let's say this was called as A, this is called as flop B. Okay. Now when, for example, we are taking a path and analyzing it between the flop A to flop 1. Now the same flop which you were considering as launch flop will become capture flip-flop, correct? And this flop, which is now launching the data, will become a launch flip-flop. So every time you cannot, if someone asks you like, what is launch flip-flop in the design, you say that when you're considering a particular respective timing path, during that analysis, the flop which launches or sends out the data is the launch flip-flop, and the one flop which receives or capture the data is called as a capture flip-flop. Okay. Now, for example, what is this the circular box between two flops, which is the launch flip-flop and capture flip-flop, is called as? How do you guys term it? Guys, you would have done this more. Pardon?
Combi path.
Combinational path. Okay. And that's why you call it as a combo logic path or combinational path. Okay. Now see, it is not called a standard logic path or something. Understand why it is being called as combo logic path. I stated, right, the major bifurcation that you can do between a standard cells is to place them in two major units, is either combinational unit or a sequential unit. Okay. So all the cells that are going to be present in this, whatever you circular box you see, right, are going to always be your combinational cells. Okay. Your and, or, not, marks, okay, AOI cells, OI cells, whatever these cells, these are all your combo logic cells. Okay. Now, whatever the delay that is being accounted because of these cells, you call it as the total delay, which is contributed by the logic gates between the flip-flop output of 1 to the input of flip-flop 2 is called as nothing but your combinational logic delay. Okay, understand? See, these are all the terms that will be very useful when you go ahead, right? Because I have seen a lot of people who are messing up with such small terms. Okay. Now, let us understand, for example, there is a, what is actually a clock path? Can anyone just explain me? You would have understand there are two different paths. One is data path, one is clock path. From the naming itself, it is very clear. Can just anyone explain me what is Data path and what is clock path?
Yeah, whatever the path which is going to the sync pin of the clock sync pin of the flop, that is a clock path from the clock source.
Okay. Okay, and what's data path?
Data path, whatever the path which is going to the input pin of the flop, that is a data path in rest to rest logic right now.
Okay, in rest to register path, whatever.
From the clock pin to D pin.
Okay, from the clock pin of your launch flop. See, this
To
is the
the
way I'm saying. Whenever you're trying to explain, give it in this. See, even if guys, if you're appearing for the interview, you have to be very crystal clear, stating what is launch flop, what is capture flop, from where, which point it is going to the which point. Okay. Now, when I'm stating it in a very bigger bucket, you bifurcated one path as data path, one path as your clock path. Okay. Now, this clock path can also be segregated into two paths. Okay. See, your launch flip-flop and capture flip-flop both will have a clock pin. Okay. Both are sequential cells. Okay. So now, whatever paths it takes, from example, let's say this is a PLL. Let's not say even it's a PLL. Let me make it to a very smaller unit. And this is a clock port of your design. Okay. CLKM is nothing but your clock port of your design. From here, the clock will be entering in your design. Now, the clock has to traverse and reach to each and every flop of your design. Okay. There is no exception that it won't reach to any flop. Okay. So it has to traverse and go and end at the clock pin of all your flops. Now, when you are considering a specific path, now in this case, we have considered a path which is between register to register. Correct? Now, if you look at it, there is a path from this clock which is going to the clock pin of your launch flop. And there is a way the clock is being traversing from your clock port to the clock pin of your capture flop. So you have to segregate and say that the clock path can be divided into two categories. The path taken by the clock to reach from the clock port to the clock pin of the launch flop is called as launch clock path. Okay. And the path traversed by the clock to reach from the clock port to the clock pin of the capture flip flop is called as capture clock path. Okay. And now if you then we'll go too much into detail, maybe understanding of maybe during STA lectures, there will be something called as CRPR. Okay. So common clock path pessimism removal. So that time you will understand why it is being used. Okay. Now I am making you just aware with the terminology. Okay. So now if you look at the picture, right? The path taken by the clock path to reach the launch flop, even at the capture flop, there are two buffers which the clock traverse same. So since it is common both to the launch flip-flop clock path and to the capture clock path, it is called as common clock path. Okay. So now what we understood in this complete lecture is, what is a launch flip-flop? A flip-flop that sends or launches a data signal during a clock cycle. Capture flop is the one that receives it or captures it. Combinational logic delay is nothing but the total logic delay of the gates which is present between the output of your launch flop and the input of your capture flip-flop. What is your launch clock path? The clock path which is taken from the clock source to reach to the launch flip-flop. And similarly, to reach to the capture flip-flop is nothing but your capture clock path. Okay. Now, if I go in detail, let's understand what is with respect to the word latency. Okay. Now, in a layman language itself, also you can understand what is latency. Can anybody just let me know what in a layman language, how do you define latency?
It's actually delay.
Correct? Delay. In our layman language, we say it nothing but as a delay. But here, with respect to the VLSI, we have started using various different terminologies, which is called as latency. Okay. Now, this latency, when you look at the bigger picture, for example, the box which I have drawn, right? A white box, maybe something is a block which you are working upon. Okay, see, when you're working in an industry, there is a big SOC. Okay, your block maybe some initial, let's say, for example, within the complete mobile chip, there is an audio unit, there is a video unit, there is a display unit. Okay, let's say you're working on one unit which is called as camera unit. Okay, it can happen. See, there is a possibility that the logic which generates your clock, either it's through PLL or your crystal oscillators, whatever is that, it can happen that the block which you're working upon has the clock generating circuit. Okay, and it can also happen that the unit which you're working upon doesn't have this unit, PLL or crystal oscillator. The clock generating unit is in some other block. Okay, now if you look at this picture, okay, whenever we as a person are working, we are always intended, we are called as, in industry, you're called as a block owner or you're called as a partition owner. Okay, so when you are working, you are always working on this white box. Okay, let me say that this is called as, let me say this is called as block A. You call it as a block A, design A, whatever is there. Okay, you're working in this unit block A. Okay, so the point through which, the point is nothing but the port through which the clock enters in your design is your clock port. Okay, see, what all signals can enter in your design? Just understand from a VLSI perspective, what are the possibilities of different types of signal that can enter in your design? Guys, are you awake?
Signal,
I'm like,
clock signal, power signal,
clock signal, power signal,
data signal.
data signal. Okay, we only can have these three kind of bifurcation, correct? One is clock. See guys, when you looked at even at your left and everything, you remember that the use signal, use power, use ground, correct? The signals can be bifurcated into two major. See, there are different ways you can bifurcate a signal. You can also call it as your signal is an analog signal or is a digital signal. Okay. Now, when you're saying it is bifurcated into clock signal, data signal, and your PG signals, which are nothing but your power ground. Correct? So the port through which your clock enters is called as clock port. Okay. Now, let's say this, the point I have given, this is your clock definition point with respect to your block. Okay. Now, once the clock is arriving here, see, when you're looking at a layman language, now you can see, okay, the clock will just traverse. It is not a very simple traversal that, okay, with just a metal wire, it will make a connection to the clock pin. It will have to, when you're building a CTS, correct? You will have a lot of, let's say you're building the CTS through buffers and inverters. So there will be a lot of clock buffers and clock inverters, correct? Now, what happens is when you're at any, see guys, you have to do an STA even at your, before pre-CTS stage, right? Even at your synthesis stage, you are performing STA. Even at your floor plan stage, at your placement stage, also you are performing CTS, correct? So before CTS is being done, we will go into exact what is complete PNR flow later. But understand that, for example, because now since your design have not reached the CTS state, you need to model something, correct? See, I know once my design is ready, it might take, let's say 10 ns. Okay, let's say it will take 10 ns delay to reach my clock signal from this clock port to the clock pin of the design, correct? So that delay you are terming as network latency. Okay, because in this your design, you are only intended to look how much delay I have for the signal to reach from the clock port to the clock pin of my flop. So that is termed as nothing but your network latency. Now, when you look at the bigger picture, right, the clock has to even reach your clock port. See, the constraints also keep on changing. Block level constraints are different. Chiplet level constraints are different. Okay. So what happens? The clock has to even take some amount of delay to reach from your PLL, or well, let's say PLL or crystal oscillator, through whatever source you are generating the clock, right? It will take some time to traverse, and that is called nothing but your source latency. Okay, so very simple terminology, you understood that. Source latency is the time taken by the signal to reach from the origin or your PLL or your clock generator circuit to the clock definition point in your design. Okay, and network latency is the time taken by the signal to propagate from your clock definition point to your clock pin of your flop. Okay, and now what is total latency? When I'm asking what's the total latency in your design, what would be it?
Network latency plus source latency.
Correct. It will be a combination of network latency plus your source latency, correct? Okay, now let me go ahead. So we understood what's the definition of source latency, what's the network latency, and you understand that the total clock latency is nothing but the combination of your source latency plus network latency. Guys, understand this. I'm not going to revise it when we are doing a complete STA or when we are going through the CTS stuffs, right? These are all the small terms which you feel are is of no use. But many of the times the interviewer try to play with these all things. Okay. And this I'm explaining you because the next lecture would be a deep dive on SDCs. So you need to understand what terminology I am referring to there. I won't go back and try to explain you each of these terminologies. Okay. Now, there is one more term that you would have heard upon, which is called as something as insertion delay. Correct? Now, it's just a very different way of annotating it, but it's nothing. What happens is in industry, what it try to state that if you are saying something which is before pre-CTS stage, I will call it as latency. Okay. This I'll call it as source latency. I'll call it as network latency. But once the CTS is done, when the clock buffers, clock inverters are inserted, and clock is reaching to my all the clock pins of my flop, I will just call it as insertion delay. Okay. So there is nothing. Now, if you see the source delay over here, pre-CTS, whatever I mentioned, source delay, now this will become your nothing but your source insertion delay. This will become your source insertion delay. And whatever the times it is taking for this, it will become your network insertion delay. Just a tweak of this, but this is the way the industry try to refer it. Okay. But it is nothing. Latency is nothing but in a layman language, understand the delay. Okay. Anyone have any doubt over here?
No.
Okay. Now let's go to the next concept. Okay. Now the next concept states something as, for example, clock skew. Okay, you would have been familiar with respect to the clock skew. Can just someone explain me? Well, now I'll pick it up. Someone else. Don't. I think everyone at the time. One person is only answering. I have two Shiva now. The one with SHIVA. Are you there in the call?
Yes, ma'am.
Okay. Have you heard the word skew?
Yes, ma'am.
Okay. Just can you explain me what you know about skew?
Yeah, skew is the difference between the arrival times between the launching clock and arriving clock.
Between the arrival of your
The difference between the arrival times of the launching clock and capture clock. Sorry.
okay capture clock path and your launch clock path. So earlier we had looked at a diagrammatic representation where I was stating, right? Now you understand that in, for example, if I go, I'm not able to go back. Okay. Now guys, over here with respect to this diagram. Okay. Now let's say I am giving a number to all this buffer stating 1, 2, 3, 4, 5, 6. Now the one without H, Siva. Are you there in the call? Guys, I don't want anyone to be sleeping in this lecture. That's why I'm taking over the name and asking so that you all guys have your ears open and your eyes also open. Shiva, you're there, correct?
Yeah.
So Shiva, now you are, first let me know, are you aware about this term skew?
Yeah.
Okay. Now explain me the skew with respect to this diagram.
The skew is nothing but arrival clocks of two sequential elements, nothing but launch and clock from the clock source. Nothing but launch clock source is the flop 1, 2, 3, 4 is the launch, and
1,
1,
2, 3,
2,
4 is the launch.
1, 2, 5, 6 is the capture. Between the delay between these two paths is the skew.
Okay. So understand guys, skew is always, don't get confused with the term skew and slew as well, right? Slew, we understood it in the last lecture that how is your input transition been calculated, correct? The slew is nothing but it's how does your signal vary with respect to the time. Okay, it is done like we have 30%, at what time the signal was at 30%, and at how much time it took to reach to the 70%. Okay, Now this is skew. Skew has to be always between two different flops. Skew is never with respect to one flop. It's always with respect to two different flops. Okay. Now you have heard about it when you're doing all the calculation. You do T skew nothing as the difference between your let's say it will go. Okay. Now see the time difference between arrival of the same edge of the clock signal at the clock pin of two flops I have mentioned. One is at the capture flop and one is at the launch flop. Theoretically, the definition, the formula to calculate the clock skew is nothing but your capture flop latency minus launch flop latency. Okay. Now you understood. Now I won't be using the word as delay or something. Capture flop latency and your launch flop latency, which is nothing. How much time did my signal, clock signal, okay, now you be very specific, clock signal took to reach to the capture flop minus how much my clock signal took to reach to the launch flop. Okay, let's say, Pavan, you are there? At least you are there now. You are not there if you are not on the older meeting. You are there in current meeting, right? Can you unmute yourself? Pavan, guys, you think that I am just not, I am noting down the names of all the folks who are not answering me.
Yeah, ma'am.
You're there, correct?
Yeah, ma'am.
So you understood how to calculate the skew, correct?
Yeah, ma'am.
Okay. Let us go to the back example and you'll only help me to calculate what's the skew. Give me a detailed explanation one by one. First of all, what's the formula to calculate the skew? Pavan, I'm waiting for you.
Yeah, T capture. Timing of the capture flip-flop minus launch flip-flop.
Timing?
Time
It's
period.
time period. Guys, understand. See, these are all the words I'm not saying. Time period or it's the delay. Period is what you, when you draw a clock, how do you draw a clock and then you define that I have, let's say, a clock of 10 nanosecond, let's say 10 nanosecond. This is your time period. Okay. The clock will come with, the clock has an attribute which is a period. It has its characteristics. Okay. What is clock period of launch flop? Who was answering it? Pawan,
Data
where are you?
signal. Data signal
I
we are
won't.
reaching to the clock launch.
Yeah, so
And the data
I'm
signal
saying,
we are reaching to the capture.
so where did the Pawan
Period
go?
is different, launch is different. The time period is different. Sorry.
Correct. So you have to use it. This is the only way. See, the main intention of my this complete lecture, please guys use the proper terminology. I have seen lot of candidates who have failed the interview because they use the wrong terminology. They have a complete idea what it is, but they have used, for example, instead of delay, they use the word period. Okay. For example, let us now, I will take one by one name. I don't want any. Darshani, you're there? Darshani, can you unmute yourself? Darshani is also not there.
What's meant by
Okay.
the skew group, no?
Hello? Somebody
And
saying
what?
something?
Yeah, ma'am. Ma'am, what is meant by the skew group, no?
See, that explain, see, I'll go step by step. You cannot ask me like one thing as STI, I have to explain you what is the skew grouping and everything, correct? That is with respect to the complete CTS concept. I'll explain it in a different way. Okay, there is a complete format structure which I have. For now, as of now, to explain the basics SDC, I have given you this way.
Yeah,
Okay,
sure, ma'am.
skew
But
grouping is
since
mainly.
the okay, ma'am.
Okay, so guys, now I just wanted to please do attend the lecture and keep like be attentive in the class. Okay, The main intention I am giving is because going ahead, I will directly use the word latency, skew, group, or whatever is like capture flop, launch flop. If you're not aware of this, everything will go above your head. Okay. So now for this, we understood that the clock skew is nothing but the difference between the capture clock path delay and the launch clock path delay. Now, the capture clock path, let us say all of these buffers that are there in my design are having a 1ns cell delay. Okay, so now let us capture it. So how much will be my T capture delay? 1 plus 1 plus 1 plus 1. It is how much? 4ns. Okay, and for T launch, how much we will have the delay? It will be equal to 4ns. Okay, now if you look at what will be the skew value?
0.
0. Correct. So this is the way, okay, to how to calculate the skew. Okay, now let me go ahead. Now understand, okay, there are different types of skew. Okay, so let us say whatever we discussed in the earlier diagram, right? I say that the skew is always going to be between two different flops. Okay, now whenever you are considering a flop, whenever you're considering a timing path in your design, you have always considered a reg to reg path. Okay, in that reg to reg path, one is your launch flop, other is your capture flop. The skew between the launch flop and the capture flop of the same clock domain, okay, you will call it as local skew. You're terming it as local because within that localized timing path, you are calculating the skew. Okay, both of these flops are related with respect to the clock pin. Okay, so whatever we calculated in the earlier diagram was nothing but your local skew. Then there is one more terminology which is called as global skew. Okay, now it can happen. Now imagine it in terms of a bigger diagram. Okay, what happens is in your design there will be let's say around 100 of flops. Okay, a clock port will be one, whatever. Let's say that, for example, I was making a, let's say this is your block. Okay, and let's say, for example, I'm giving a very hypothetical situation. There is only one clock port. Okay, now this clock port is driving, let's say there are, I will draw at least, guys, whatever is in the cross marks is nothing but your, let's say, are all the flops. Okay, let's say these are your flop from 1 to, okay. Now, whenever we were considering a particular timing path, we were localized with respect to, let's say I was analyzing this timing path from reg to reg. Okay. Now, whatever happened is within how much time my clock took to reach over here, there will be clock which is going to over here. Clock will be going to all the clock pins in my flops, right? Let's say it has reached finally to over here. Now we were calculating a localized skew. So we term it as a local skew, which is a difference between the delay taken by the clock to reach to the capture flop minus the delay taken by the clock to reach to the launch flop. Okay. When you look at the bigger picture, clock is reaching to all the flops in your design. So it can happen that it might take some, let's say here only one buffer was there. So it took around 1 ns. Now let's say to reach to the flop 9, there were 5 buffers. Okay. So now it took 5 ns to reach to your this flop, which is flop number 9. So now the difference between the clock to reach to the flop 9 and to the flop 1 is nothing but your global skew. Okay. Now, for example, let me first erase it. Okay, so now understand that your local skew is nothing but the difference in the arrival of the clock signal at the clock pin of the related flops. Or you can say within the particular, whatever timing path you are analyzing, because the clock pins are related. So that's why you term it as a local skew. Okay.
Ma'am, related
See, related
these are
is because I'm saying with respect to the
same
one
delay.
time. Pardon?
Ma'am, that related flops means they are having same delay or they
No,
are connected
they
with
are
data
having
transfer.
the same clock. They are operated by the same clocks, and that's why we are saying it's with respect to the same. Since the clock is same, these flops are related to each other with respect to clock. See, when I drew it in the older diagram also, if you look at it, same same clock is reaching the flop, correct?
Yes, yes, yes.
Okay, so how are these both clocks related to each other? With respect to the same clock, right? See, understand, in the real world, there won't be one single clock in your design. Okay.
Okay.
There will
Sometimes,
be there are multiple clocks in your design.
sometimes the
Anyone see?
related flops can have the two different clocks, no, ma'am.
Then it is a clock domain crossing. That is a different concept. Okay, but that
At
time
that time, we can't say it's a local skew.
that's a different concept where you call it as a clock domain crossing. Then you have to do a synchronizer and all different steps is there. Okay, but when you refer to the clock skew, right, you refer it with respect to particular clock. That the clock skew of, let's say, clock A in my design, local skew of clock A in my design is 1 ns. Global skew of clock A in my design is 3 ns. So with respect to the clock, you have to state it, correct?
Okay.
Hello?
Okay.
Yeah. Now we understood the next thing, which is nothing but your global skew. Okay. Global skew, you can call it with respect to non-related flop. Why I'm saying it non-related flop? Because see, if now when you looked at a bigger picture where I drew, right, they were not directly correlated to each other. If you looked at whatever diagram I drew, 1, 2, 3, 4, 5, they were not directly correlated to each other. Okay. Then I can say that the global skew in my design, out of the complete clock is so and so unit. So if you have to calculate it, right? Now let's say this is the, for example, this is the way. For example, I am saying this. Okay, this is the clock port of my design. Let's say this is a clock A and it is reaching to the flop 1. There is a capture flop reaching to the flop 2. Okay. Now, if you have to calculate the local skew, okay. So Teja, can you unmute yourself? Teja, are you there?
Yes, ma'am.
Okay, Teja. So can you just help me to calculate the skew for this diagram, which I am explaining?
Skew will be 1 nanosecond.
Skew will be 1 nanosecond. How did you calculate it? Explain me.
Delay at capture flip-flop clock minus delay at launch flip-flop clock.
So delay at the capture flip-flop was 2 ns, correct?
2.
And the delay to reach to the flip-flop 1 is
1 nanosecond.
okay. So now you can say that the localized or the local skew in this diagram is 1 ns. Okay. Now let us understand with respect to this. For example, Satish, you are there?
Yes.
Okay. Now just help me to understand, for example, within this entire design, let me say that I had 3 flops. Okay. Now can you explain me what is the global skew?
Uh, total delay of 5 ns is there in capture flip-flop.
Can you just explain me how there is a total delay of 5 ns?
Here it is two flip-flop are there now, D and FF2 and FF3. Both are 2 ns, downs are 3 ns.
Okay. So 2 ns plus 3 ns is equals to 5 ns you're stating.
Yes.
Okay. So that is with respect to your capture flop you're stating.
Yes.
Okay. And with respect to the launch?
Launch is 1 ns.
So what's the skew?
Skew with 4.
5 minus 1.
Yeah.
Okay. So guys, understand it. When I said at the start that skew is always going to be between two different flops. Okay.
Yes.
You cannot
Yes.
sum up the flops, correct? You have to take it only with respect to two different flops. Okay.
Yes.
Now you have to understand it that the global skew is always calculated from the entire design. What will the tool do is calculate the latency which is highest. And the
Okay.
highest latency will be of nothing but whatever is your longest clock path delay. Okay.
Yes.
Now don't consider every time you see, that's why I said you bigger picture. When you are
Okay.
looking at it, you are looking this at launch, this as capture. You are looking
Okay.
at this as launch, this as capture. Now just take each of the flop as just that the clock is reaching at it.
Okay.
So which is the flop which is taking the longest delay?
Flip-flop 3.
Flip-flop 3. Correct? And how
Yes.
much delay it is accounting to?
3 nanosecond.
3 NF.
3 ns, correct? And which
Yes.
is the flop which is taking the shortest delay?
1. Flip-flop 1.
1 FF1.
The flip-flop 1. So how much delay is it accounting for?
1 ns. So
1
global
ns.
skew is 2 ns.
Correct. So always understand there. See this picture very. I have shown it very like there will be no design with only 3 flops. Okay, understand there will be more than thousands of flops in your design. Okay, so whenever somebody asks you about the global skew, right? It does
Yes.
nothing but it calculates from the clock port which is the one which is taking the highest delay or the longest delay clock path, and the one which is taking the shortest clock path delay, and it will do a simply subtraction of it. Okay.
Okay. Okay. Got it.
Now, so understand that the global skew is nothing, just a simple definition for you to understand longest path delay minus the shortest path delay. Okay.
Hello.
Now,
Hello.
hello.
Can you differentiate between related and non-related flops? So in the previous slide, you were showing like there are two categories, right? So one is like related flops and non-related flops. So how will they differ in the definition?
See, it can happen. For example, these two flops are not. When I have to draw a diagram.
No, I mean just wanted to understand like how do they differ by definition?
See, why because they are not directly in contact with each other. When you have to refer with the local skew, right? You are stating these two are correlated with each other because the output of one is getting as an input. So they are having a relation because both of them are operating with respect to the same path. Correct? Here,
Okay.
I am not stating the output of this is getting correlated to this. It might go to somewhere else. This is not necessarily like the output of this, whatever is going, it's going to, let's say, flip-flop 4 over here, going over there, and it goes to the output port. So is there any correlation between the flip-flop 1 and flip-flop 3?
Okay. Yeah, got your point. Yeah.
Correct. So understand it. Like, see, this word is very tweaky to understand it. So that's what I'm saying. For a layman person, just understand local skews, whatever path you are analyzing it, you have to see. I'm not sure. I'll take a lecture on making you understand different types of timing paths as well. Okay. Rest to edge, we call it that.
Yeah.
Okay. Whenever you are analyzing a rest to edge path, okay, whatever is your launch path delay and whatever is your capture path delay, you subtract it. That's the local skew. See, you have to understand how the tool does this reporting. The tool will be dumping all this when you do the report skew, report clocks. It will give you all this type of things. Okay. So what tool does it? Whatever paths you have calculated, it will do it. Global skew, it will be with respect to the complete design. For example, you want to know that what is the longest path you have taken, right? Then you will try, for example, the skew is very high. So I will try to optimize it based on this. I will try to bring this flip-flop 3 closer. See, there are targets which are being provided that your skew should not go beyond this much. Your latency should not cross this much. That's the main target you're meeting when you're designing CTS, right? So when I understood that, okay, the highest delay accounted by my capture clock path is, let's say, 3 ns. No, I have a target of 2.5 ns. Then you will try to make a strategy and bring it closer to near to that so that it doesn't make a lot of transition and have a higher delay. So since these flops does not have a direct relation with them, we are calling it as non-related. Okay.
Yeah, got it. Yeah.
Now there are even, see, this is a very too small bifurcation I have given you with respect to local skew and global skew. Okay. Now there is something you would have always heard, something called as positive skew, negative skew. When we'll go in depth about STA, I'll explain you, because that's a big topic with related to CCD and everything, what is useful skew and a hurtful skew. Okay. So now in this lecture, we will just understand the concept of what is positive skew. Okay. From the definition itself, you would have got that the way the skew is calculated is nothing but your capture clock delay minus your launch clock delay. Now, I'll just, well, this is a very simple and easy concept. You should be able to answer it. Mani, you're there? Hello? Mani, can you unmute yourself? Guys, I'm just making it down the note of the folks who have just joined the lecture and slept away. Manish Kant, you are there?
Yes, miss.
Okay, Manish Kant. So now we will just do the simple skew calculation, no rocket science. Can you explain me what is the skew over here? Give me a clear-cut guideline. So what is the capture part delay, clock part delay, what's the skew?
The capture part delay is like this clock pin and clock tree bus.
Let's say, for
Clock
example, you
tree
want me
buffer.
to annotate it with some, let's see, I'll call it as 1, 2, 3, 4,
Yeah,
5, 6, all having 1 ns delay. Now explain me.
yeah. Ma'am. So this one is a capture flop delay. Yeah, ma'am.
So it
And
accounts to how much ns?
1, 3, 4. Sorry, 3, 4, 5.
5 ns. Okay.
5, ma'am.
So capture clock delay is
Yeah,
5 ns. What's the launch clock delay?
5. And launch clock delay is 1, 2, and 3.
Correct. So it's 3 ns. So what's the skew?
Yeah, yeah. 3 minus 5, ma'am.
So it is positive 2 ns, correct?
Yes, ma'am.
So since it is a very positive number, we just call it as positive skew. Understand? There is no rocket science behind it. Okay. If the subtraction you're doing between the capture clock delay to the launch clock delay turns out to be positive, you call it as a positive skew. Okay. Now to understand it, for example, let me say almost all the folks are done. Nobody else is there. Okay. Pawan, you are there?
Yeah, ma'am.
Okay. So I need you to explain me for this one. Okay. Can you explain me what's the delay over here?
Capture flop is for delay is 3 ns and launch flop is 4 ns.
4 ns. So what's the skew?
Skew minus 1 ns. Is
Skew
negative
is
skew.
minus 1 ns. Correct. So since the
Yeah.
skew turned out to be negative, you call it as a negative skew. Correct.
Yeah.
So understood that there is no rocket science behind it, but the thing is, this will be too much useful when you're doing your complete STA analysis, and when there will be an interview questions revolving around which skew is good for which analysis. Okay. There are two major broad categories of analysis we do in STA. One is setup analysis and one is the hold analysis. Okay. Now, for example, if I have to give you a dramatic this, right? Guys, how many of you are aware about this, at least basic setup and hold? Almost everyone?
Yes,
Yes.
ma'am.
So you have a basic notion of what is setup, and I don't want to go in depth, but at least you have a great understanding on what is setup analysis, what is hold analysis, correct?
Yes, yes.
Okay, let us come over here. Let's see here. Okay. So for example, you always know that the setup check is primarily done. See, why this is definition, I wanted to know, because you should not get confused why I'm pointing setup check and this hold check. If you're aware about it, you know that the setup check is always done one clock cycle after the launch edge. Okay, primarily it is done. Then you play with something which is called as exceptions, where you can make it as a multi-cycle path. Don't please check after the 1 clock edge. Have at least 2 or 3, whatever you gave it, it checks after that. and whole check is always done on the same cycle. Now, just to explain you have heard like positive skew. So whenever this timing diagram comes, right, sometimes what happens is see, since this I have wrote it as positive skew, you're able to understand it. I could have erased it. What happens is I've looked at when I in the interview I gave and asked the people about, can you explain me what this diagram tries to state, what skew it is, they get fumbled it. So just understand, when you are saying something with respect to the skew, when you said positive skew, okay, see, when you were trying to say something as positive skew, what we had is, for example, T capture clock delay minus T launch clock delay, and it turned out to be positive. The meaning of overall thing is positive is that your T capture clock delay was greater than your T launch delay. Greater, it means it arrived late and this arrived early. Okay, so the same thing, just in a diagrammatic way, when people I'm asking them, they become confused. Okay, so when somebody gives you this diagrammatic representation, understand, if the capture clock is coming late and the launch clock is early, it's a positive skew. Okay, now in the opposite diagram, which clock should come first when I have to denote something as for negative skew?
Then capture should come first.
Correct. Then the capture should come first. Okay. Correct. Your capture should come first and then your launch should be there. Okay. And in the case where we solved the first example, where what did your skew turned out to be? 0. Correct. In that case, you will have your launch clock and your capture clock at the same time. And this is always an ideal scenario. It never happens. Okay. For example, just think on from your end, I just want to think of it. If it could have happened, was this an advantage for us? See, let us assume that the ideal case that both clocks would have arrived at the same time, correct?
Yes, ma'am. That it is then very advantageous.
Correct. It could have been very advantageous, but in reality, this ideal things never worked, right? But think of it from one more perspective, that if it could have happened that the clock which is arriving, let's say that your ideal case is what does it mean, right? It is stating that the delay, when I have to draw it in a bigger perspective, right? I'll just explain you. For example, I'm saying with respect to real design, let's say there are 100 of flops. Okay, 1, 2, 3, 4, everything, let's say till 100. What it is trying to state that where the clock pin is reaching each and every flop at the same time. I'm not saying 0. Skew means 0, but the delay is same. It is taking, let's say 5 ns of delay same. Okay. Within this flop also it reaches 5 ns, 5 ns. Somehow you made the design that even at the 100th flop, it is written at the same delay. Now look at the concept of power dissipation, which when I gave a demo lecture at the start, right? You would have understand that the major contribution in your design is because of the dynamic power dissipation that happens. Correct? And when you looked at the formula of the dynamic power dissipation, you know that dynamic power dissipation depends upon alpha F C VDD square. Okay. Now look at it. If all of the clocks are reaching and switching, all of your flops are switching at the same time. See, switching means, see, understand what a flop does. It once it gets the clock, your D pin will become transparent. Whatever is at the D, it will go to your Q pin. Okay. Now understand that all 100 of the flops are switching at the same time. So understand the amount of power dissipation. It will be very high. So with respect to the power terminologies, if in case the skew was 0, it could have been a disadvantage. Okay, so understand it with this perspective also, that with respect to timing, it would have been good. But with respect to the power, you would have a lot of higher dynamic power dissipations. Correct?
Excuse me.
Yes, ma'am.
Ma'am, but that is the goal of the CTS, no, ma'am?
The goal of CTS, if you would have ever looked at it, it is never to say that you should have 0 skew. You would have looked at it as a minimal skew.
Yes, yes.
Correct? Because in reality, no, see, at this pace, even if in real world, if you could, it is impossible to achieve this. Okay, that's why, see, if you look in the industrial perspective, there is no skew which is hitting 0 ns. Okay, that's why I'm saying the reality in the real world is either it will be either having a positive skew or the negative skew. We say a target to minimize the skew. We don't want a huge difference in the skew. Okay, so the main target of CTS is never to make your skew 0. They have a target of range, and that's why we say that we have to make it within this target and minimize the skew and delay.
Okay.
Okay, in real time, if you have even in your design, just try to look at it.
Oh, sure.
Okay.
Okay.
Now, since you guys had a notion of, for example, let's say, what you call it as. Okay, that will go in, let's say, in STA lectures if I have to, like, because there are a lot of topics which are interrelated. I cannot explain everything in one go. Now, for example, I'll move on to one more topic which I want to make you aware is. It's about uncertainty. Okay. Now understand what is uncertainty. If I have to correlate it with you with a real world example, let's say, for example, a person is running a marathon. Okay. Let's say there is a runner A which is running this marathon every time. Okay. Sometimes, let's say, for a 1 kilometer race, he takes 10 nanoseconds or 10 seconds, not nanoseconds. Let's say he takes 10 seconds of delay to reach from point A to point B, which is 1 kilometer far. The person takes 10 seconds. Okay. Are you going to be very short that the next time the person runs in this race, will he take exactly 10 seconds? Can you give a bet sure guarantee?
No, ma'am.
No, right? There is no such assurity that if the person has ran first time, he can take 10 seconds. Next time, it might happen that the person can take at least, let's say, 12 seconds. Or it may happen that the next time he's running, he might take 9.5 seconds. Okay. So similarly, it happens in the real world that every time this PLL are also some machines, right? They are also having a marginal value of that they can do some error. So because of that, it can happen that the clock which is intended to arrive at, let's say, every time expecting that after, let's say, 10 seconds, I will have my clock keep on coming it. But it is possible that sometimes I might get the clock at 10.2 ns. It is possible that I might get the clock at 9.8 nanoseconds, right? So this complete, understand, uncertainty is a very relevant word in our real life, right? For example, even if it's a rainy season ongoing, I cannot say predict like tomorrow that tomorrow also it will rain that heavily that it has rained today. Okay, it just specifies that, okay, if the person has ran this race, the person might range the duration the person might take to run this race ranges between, let's say, 8.5 ns to 10.2 ns. You give a range. Okay. So similarly, in this world with respect to the clock also, we specify it like it's a specific window within which your clock edge can occur. Okay. When you consider the umbrella one word as uncertainty, you consider that it accounts for different terminologies. Like one which I mentioned is the jitter. Okay. One is we can, just to have a safer side, we also include something which is called as additional margins, just to be on a safer side. And then we account into something as Q. Specifically, I have written it at pre-CTS stage. See, once you're I said like at the earlier, when you are modeling it before the CTS stage, where you don't have a complete notion how many buffers inverters are going to be inserted, what will be their delay, you have to model it. You have to make it appear, okay, this might look at this. So you have to tell the tool, correct? Otherwise, tool will take it as a 0 second delay and might start doing the analysis in that way. But you are trying to predict it or model it with respect to the real world that will happen post CTS. Okay. Now, because of this uncertainty, the way the clock might arrive can be a bit early, can be a bit late. Okay. And whenever you're doing this timing analysis, right, whether it's a setup analysis or hold analysis, you're always taking the worst possible case delay. Okay. For example, what is actually a setup delay? Can anyone just tell me in very small or in very short, what is actually a setup?
Well, minimum time the data should be stable before the application of the clock.
Okay, so before the clock arrives, your data should be present over there, correct?
Yes.
But for example, when the tool is doing this, what will when you have this complete definition stating that your setup time has to be, that your required time has to be greater than your arrival time, correct? But in order to make the tool as pessimistic, you know about setup is called as max delay and hold is called as a min delay. Have you ever heard this terminology?
Yes, ma'am.
Yes,
Okay.
yes, ma'am.
So have you ever wondered why they are calling it as a max and why they are hold calling as min and not vice versa? Why they come up with this terminology specifically? Why max delay? Why min delay? Have you ever thought it? See, anybody is giving any terminology specific to anything, they would have given it the thought, correct?
I think, ma'am, for a setup, if maximum delay is taken into account and setup time is requirement is met, then it is applicable for minimum also. So I think max it is written.
I didn't get the way you're trying to. Okay, let's finish it off. Then maybe I'll try to say that. Okay. So now you understand the uncertainty is nothing. The way I tried to state you with respect to the person who is running a race, right? Similarly, the clock might start from the PLL. The time it might take, sometimes it can be possibly it can be early, it can be late, but we have to model it. We have to make the tool understand it. And whenever we are modeling it, we are nothing but we are making, see, uncertainty every time you would have looked at it is getting in your required time section. I'm not sure. Guys, you have started using the prime time tool or even your ICC tool and have looked at the timing reports. Your lab session has started by from your PD
Yes, ma'am.
lecture. So you have looked at the tools. You have looked at the timing report.
Yes, ma'am.
Okay. So there you have you would have looked, for example, in that report, did you look that in your required time section, you have something which is called as clock uncertainty?
Yes, ma'am.
Okay, so see, guys, this is nothing but you're making the tool a model way that, for example, it can happen. So we are trying to be pessimistic. Okay, we are trying to model it. It is not necessary that the PLL will, let's say, instead of 10.1 NS, it can happen that our PLL is so good and it is every time generating the clock at 10 NS. But we, in order to be, for us to be safer side, we are doing these calculations so that even if let's say, what if the clock arrives early? How will my timing analysis be? What if my clock arrives late? How will my timing analysis will be? Okay, so we have to take the worst situation, and in that worst situation, if I am able to meet the timing, then I am very much confident that my chip is going to work in all the conditions. Okay, so similar way I'm stating, for example, when you're doing this uncertainty, right? There will be an uncertainty for setup and there will be an uncertainty for hold. Okay. So now this uncertainty I said, right? It is calculating into account the different, for example, it is calculating what kind of a jitter, how much is the skew and how much is your setup margin. This margin is an additional pessimism which we are taking into account just for our safer side. Okay, what happens? See, understand. For example, this person has ran around, let's say, 10 marathons. Now we come to know, for example, the average between he takes is between, I said, 8.5 to 10.5 NS. But we are saying, okay, let's take a one more plus minus 0.2 NS. Okay, the person can sometimes run from 8.3 NS to 10.7 NS. So just the extra pessimistic marginal side we are taking, and we are telling the tool within this, can our timing be met? Okay, now if you look at setup uncertainty formula and your hold uncertainty formula, what's the major difference you're looking at?
Jitter.
Jitter. Now, see, understand, for example, this comes into the picture when you are looking at what edge is your setup done and what edge is your hold done. That's why I said, you guys are aware, right? Jitter is
Yes.
always between the edges which are at two different we are going to take. But since in the hold, we are doing it on the same clock edge, correct? That's why there is no concept of jitter in your hold values. Okay, now I stated once your CTS is going to be built, you will have your buffers and inverters in your network, correct? Depending upon this buffers and inverters in your network, you will have the delay accounted by each of them. So out of these three factors, think about it. Once the CTS is built, which of these out of these three values you will have the real clear picture? Let's say your correct. Once your CTS is built, you will have the buffers and inverters, and you can directly calculate what is the skew. See, that's why I'm mentioning. Look at what I have written. It is pre-CTS. I am trying to model it. Now everything was with respect to the ideal clock because I don't have the real notion how will be the clock in my design, how will be they spreaded, how much delay will they take, and still I don't know how much delay will they take. I don't know what would be the skew, but I'm trying to interpret it based on some calculation. Let's take this much would be my skew. Okay, so now once this has been done, okay, you will have your post CTS. Okay,
Once
in that,
repeat that.
hello.
Why not jitter for hold? Once repeat that. Why not jitter for hold, ma'am?
Okay, so understand. See, jitter is also something which is with respect to, let's say, two different edges. Okay, see, there is when we are, because I have all these things in my STA lecture, I will explain you in depth about it. That's why I said when you are doing a setup check, let's say an ideal case, how do you do a setup check? Hello?
Ma'am.
Hello?
Yeah.
Yeah, Venki. So
Yes,
can you just explain me how do you do a setup check?
Setup check. So requirement is arrival.
Required and arrival, I understood. But in the
Okay.
earlier diagram also where I showed case, right? For example, this diagram. Okay. If you look at it, you are always doing the setup analysis on the one clock cycle after your launch clock cycle, correct?
Yes, ma'am.
Correct. So this is the two different edge of the same clock cycle, right? The edges are different, right? For
Yes, ma'am.
example, I have to understand, let's say this is the first edge, this is the second edge, this is third edge. Same clock cycle, first edge, second edge. Now you're not doing it, the setup you're performing between two different edges. Okay,
Yes,
so the way I explained you skew is as it is related with respect to two different flops. Similarly, the jitter, which is either your, there are different types of jitter, cycle to cycle jitter, phase jitter, a lot of jitter, but they are with respect to the different edges. But when you're doing a hold analysis, you're taking the same edge, correct?
Yes, ma'am.
So with respect to the same edge, there is no need of what is jitter, correct? So that's why in your hold, you will not have jitter because it's with respect to the same clock edge. Understood?
I am.
Okay, hold is always done, setup is always done one clock cycle later with the launch clock cycle. Since it is done between two different edges of the clock cycle, you'll have an account of jitter. When you're doing the check between the two same edges of the clock cycle, there is no accountability of jitter. Okay. Now in the post CTS, since you have designed, now see, guys, when you open up the design, which is pre-CTS and post-CTS, you will look that there are no clock buffers, clock inverters in your design. Okay. There will be no direct, you will look at logical connections. There will be no physical connections of going through the flops, going through the clock buffers and inverters. But once your CTS is there, you have a complete design ready. How many how many clock buffers, clock inverters it will take. So your skew, whatever I explained you, you will have a real picture. You will be able to calculate it. And that's why we have removed the skew. Okay. From this analysis, you will understand one more thing. Just look at it. Just look at the point of a mathematics person. Every time, that's why I wanted to, when you are opening any path timing report, I would just suggest same path you open it, you will always find, this is the question when I asked to most of the candidates who are appearing for the interview. Why is the setup uncertain? I just give them a two question that is it possible that my hold uncertainty value is 0.3 ns and my setup uncertainty value is 0.1 ns? Can this combination be possible? Guys, just answer. From example, do you think I can have, let's take a hypothetical example I'm stating. I have a hold uncertainty of
No, ma'am. No, ma'am.
0.5 ns and a setup uncertainty of 0.3 ns.
No.
No. Why? Because if you look,
Because
Jitter is there
correct,
in
because there is a
setup.
role of this jitter factor, and obviously the value. That's why there is a very crystal clear statement that every time your setup uncertainty value will be always greater than your hold uncertainty value. You guys always mug up everything, huh? I have looked at a lot of folks. I have taken up the interviews of 100 plus folks. Yeah, setup uncertainty value is always greater than hold uncertainty. You just look at this. When I give you a question or when I will play with the timing diagram related stuff, right? There, this is the time where the people fumble up. Okay. So understand that the hold uncertainty value of 0.1 ns and the setup uncertainty value of setup being 0.05 ns is not possible. Okay. Just if you're not believing me, open up your timing report in your design and have a look at it. Okay. And this values, whatever we are giving at it, right? The main intention behind this complete lecture was from the next lecture onwards, we will look at SDCs. Okay. The one which I said, right? You have SDCs for your defining up your clocks, different, let's say if you have power related constraints, IO related constraints there, how do we give this information to the tool, correct? So those all information, when we will looking it up in the next lecture, that time we will explain you about what are the different kinds of how to define set clock latency, set clock uncertainty. So that lecture maybe I'll let you know when I can take up that lecture. So maybe in that lecture, we will try to go through all this for understanding because it's too late for now. Guys, are you? I'm not sure. See, everyone has to be okay. I'm not sure if one or two folks are okay. In case the lecture goes from, let's say 9:30 to 11:30 or let's say 9 to 11, are you okay with it? I'm not sure because I'm not very much sure how many of the working folks or if you folks have a college or your thesis related work. Are you okay with it or not okay with it? If any, even
Yes.
if one folk is stating
Okay,
that no,
okay.
Okay, ma'am.
I'm
no, I
okay.
want to understand who is not okay.
Ma'am,
Guys, you can be open up.
ma'am, 8 to 10 is also fine, ma'am.
When 8 to 10 is fine. I wind up my office work around 8. Even I have not wind it up. After this, I have to again jump to my office work and have to do it for 1-2 hours. So that's the only thing. I wind up my office work from at least 7:30, have a break, then I have a dinner from 8 to 8:39. That's why I'm
Okay, ma'am.
mostly free.
Whatever possible time for you, it's fine.
No, but I have to understand anyone which is not okay with 9 to 11 and it's fine with 9 to 10. Okay, ma'am, this is a feasible time because I'm not sure. See, everyone either they might also be a working folk. Okay, they can have their master's related thesis. In case any one folk also state that no, 9 to 10 is feasible, 9 to 11 is not okay. I'm okay with that. Anyone?
No, I'm 9.
Okay, 9 to 11 is okay, fine. So next time onwards, I'll keep, I'll state. See guys, don't every time expect that I might have, see, it depends upon the project to project phase that even I am a working person. So it can happen that I might not be able every weekday. I am always trying to target with respect to the weekends, but 1 hour or at least 1.5 hours within the weekdays, I'll try to go upon it. But for example, this is going on, right? Your, what you call basics classes are going on fine, right?
No, ma'am. Today it was not there.
Okay, but I think in basics lecture you have went ahead till what you call somebody was stating that they have learned floor planning. Was it with respect to because that?